So it draws the picture like this, right? With A and P. There's a tangent line. Okay. There's a tangent line. And X, A, B. Yeah, so basically AXBY is a harmonic quad. Okay. We kind of know this. So basically all it means to be a harmonic quad is that the cross ratio is -1, yeah? How else can we say it? But remember the Sumedian thing? So AP is the Sumedian.
Wow.
Okay, so the claim is AB be a chord, P and Q lie on AB, harmonic with AB, if and only if P lies on the polar of Q. If and only if P lies on the polar of Q. Oh. I guess, yeah, so another way to say this is if this line, yeah, is, so Q is there, right? So another way is this line is the polar of P, yeah? So this is a stronger statement. You see what I'm saying? So I'm saying two things simultaneously. I'm saying that if you join X and Y, right? Not only will that be the polar of P, it'll pass through Q.
Oh. Yeah.
So that's the claim, yeah? So why would you even think that that's true, yeah? So look at X. So this, so look at this. So
Yeah,
this
because
is,
they're the tangents or
they're the tangents. So these are little y, right? So the points on the circle are self-polar, right? So the little x is the tangent. Yeah. So look at the coolness of this. So little x intersect little y equals p, right? So that means big X join big Y equals little p. You see that? These are dual to each other. Maybe I should write this in green. See? So the fact that little x and little y go through P should mean that big X and big Y join through little p, yeah? Okay,
wow.
yeah. Wow, indeed.
Oh, and that's basically just using the previous lahirs, but you're expressing lahirs in terms of duality.
Yeah.
Ah, I get it.
Hmm. So even if you didn't see it was completely true right away, you can now try to prove it with kind of confidence that it is true, you know? Okay. So check out the following sequence of coolness. We have that. Let me use a color. So we have that A, X, B, Y is a harmonic quad, yeah?
Mm.
Wait, is that what's given? Um, okay, so it's not given, right? But we know that. So what are we given? We're given a harmonic set. So we're given these 4 points a harmonic, right? Right? So if we take a point on the circle, so X, right? And we join the lines from all the points. Yeah. That makes sense? Then what we get is a harmonic set of lines. Okay. So these four purple lines are harmonic. And the 4 purple lines now intersect the circle in a harmonic quad. Okay. So we already know it intersects A here, B here. So we don't know and it intersects X here, so that's why it's a tangent line. So it's just basically the same point. We don't know it intersects Y there, but we do know that that configuration is harmonic because that's the Symedian configuration. So it has to actually intersect here. Okay. So that proves that XY passes through Q. Okay. So you have this way of transforming the harmonic set of points into the harmonic quad. Okay, and what are we trying to prove again? That's
I think
yeah, so
there's, like, you need to draw the polar of Q, because I don't think that's on this diagram yet.
mm,
And you want to show that P lies. So you want to show that an equivalent statement to saying that A, B, Q, P are a harmonic set of points is that P lies on the polar of Q. I think that was the statement.
yeah. Okay, so what we have now is that Q lies on the line joining X and Y, yeah? The question is, do we know that that's the polar of P?
Yes, by duality, right?
Mm. A point lies on the polar if and only if X lies on the polar. Hmm. Yeah, I guess the question is, have we proved that duality?
I think that the proof of the duality is basically Lahir's, because it's like, because X is its own polar, Y is its own polar, and so big X lies on the polar of P if and only if P lies on the polar of X, which is the tangent line.
Oh, very good.
Yeah, and then Y lies on the polar of P if and
Oh,
only if P lies on Y's tangent line.
All right, so we have saved the day. Look at this. So Yi says, so Lahir's was if X lies on, well, we'll use lies on kind of abusively a little bit. X lies on
That
P. All right,
wait.
let me just write it properly. P lies on X if and only if X lies on P, right? That's Lahir's.
Mm.
So we have that. Look at this. So P definitely lies on X, right? So therefore, X lies on P, yeah?
Yeah.
And P definitely lies on Y. So therefore, Y also lies on P, right?
Mm.
So we kind of, so Yi basically proved this duality for any two lines, right? Because now if X and Y both lie on P, that's the line P has to be the thing going through X and Y, right?
Yeah.
There's only one line that goes through these 2 points.
Mm.
So this is equal to the polar of P, yeah?
Yes.
Which we just showed it passed through Q. Wunderbar.
Wait, what is Q? I still wait. What?
Q.
Yeah.
Our Q is defined to be something that makes A, B, P, Q harmonic.
A B P. Ah, okay.
And so then it has to be the line that goes to X and Y because it's a harmonic quad, yeah?
Cool.
And then we just showed using, well, you just showed using the Lahir's theorem that the line going through X and Y is the polar of P.
Ah,
Yeah, so more generally, you can be confident in using this duality as a theorem. So whenever 2 points lie on a line, their polars intersect at the pole of that line. Or conversely, if two polars intersect at a point, if two lines intersect at a point, then the poles of those lines meet to give you the polar of that point. These things are much easier to probably say and think about than listening to. We are now ready to state one of the most profound theorems about cyclic quadrilaterals. Man, we better state this before the thing is finished.
profound.
Yeah. I mean, if it's profound, we should state it. All right, profound coming up. A, B, C, D, arbitrary cyclic quad. See, when people draw a good circle, no one says anything.
Wow.
Squares in a circle,
I didn't see it.
center O. You set P to be the intersection of A, B, and C, D. Oh, crap. Okay. That's P, yeah? Q to be the intersection of B, C, and DA. I should have seen that coming. So this is a complete quadrangle. A complete cyclic quadrangle. Oh, not quite yet.
Quadrangle.
So this is Q. R is the intersection of AC and BD. Okay, that's an easy one. This now is complete. This is R, yeah? 6 lines. Then PQR are the poles of QR, RP, PQ. In particular, O is the orthocenter of PQR. That is crushing.
PQ. Oh, dang.
Wait, let's see this one. O is like, let's make O green. So PQR is, I guess, what we'd call a self-polar triangle, okay? Which means basically the polar of P is the side opposite P. Oh, so these are called the diagonal points of a complete quadrilateral. Flashbacks. And with orthocenter equal to O, what the insane. The orthocenter of that triangle is equal to O.
That's pretty cool.
Yeah. Wait, is that obvious from the statements? Ah, see, can you see why the orthocenter is the O? I think the orthocenter follows because if you join O to P, right? It's perpendicular to QR, yeah?
Wait, how?
Because QR is supposed to be the polar of P,
Oh.
yeah?
Hmm.
So can you see OP is an altitude basically of the triangle.
Yeah.
So
Okay.
similarly, O it's like OQ is the altitude of the other one, and so it's the orthocenter. Yeah, actually, the comment is kind of cool. So if you didn't care about the polar bit, right, you just wanted to say that the orthocenter of the triangle is the circumcenter of the original circle, right? That's a very like kind of elementary statement that only involves a cyclic quad. Oh, so one of the problems for this section, which is an exercise, is prove Lahir's theorem, which we already did, right? Another one is, maybe I'll write them in the last 2 minutes. But so what's left in this section is the proof of that and these two lemmas. Lemma 9.27, problem 9. I'm gonna call it an exercise. Self-polar orthogonality. So suppose P and Q are points such that P lies on the pole of Q and hence Q lies on the pole of P. Alright, why are they saying pole? Should they mean polar? Prove that the circle with diameter PQ is orthogonal. Oh. So you have a circle. Maybe I'll just write that problem up. This next problem can wait. So points P and Q. So that's the diagram that you had before. Oh crap. Something like that, right? Q. Q prime, P prime. Prove that the circle with diameter PQ, this circle here. Oh, it might go through Q prime actually, right? Oh, what? It goes through P prime as well. Yes. Is orthogonal to. Well, I think we've kind of. We sort of proved it. So this is omega and this is gamma. Prove that omega and gamma are orthogonal. Okay. All right, would you look at the time? So next week we'll finish the self-polar thing from this lemma, the proof of the triangle thing with the orthocenter, and this other exercise. And then we can continue to Pascal's theorem. Okay, I imagine some people might want the recordings of this because you've missed so much, but yeah.